So welcome to our third topic in microcontroller technology, and that is the digital control system. The digital control system usually uses a computer, a digital computer, and a digital computer consists of three major components. And the three major components are usually, one of them is the central processing unit. One of them is the central processing unit. Central processing unit. And also we have the program and data. And then thirdly, we have what we refer to as the data and memory. Data and memory. Other components that may also be very, very important is the IOs, that is the input-output system. The CPU usually controls the flow of information between the components and the processed data, between the component and the processed data. So let us just look at what the control system in the digital control system usually entail. And we are going to look at it with reference to the conventional control system that we know. That is what the control system that we know is. That is the controller. Then this is the actuator. Then this is the processor plant. So when we look at the digital control system, of course, that is the sensor. That is the line for the feedback. So that is R. This is the error. And this is the feedback B. So when you talk about the digital control system, then in this case, we simply use a digital computer. And the digital computer will simply replace these two. That is the controller and the, so here we are going to have the digital computer that is going to replace the controller and the comparator. And then because we are dealing with, at times we deal with the digital signal, then of course there will be a need in order to convert the signals from either digital to analog, depending on whatever is needed. Like in the first case, for us to have the digital computer, we are going to convert along the feedback line. We are going to convert whatever signal that we have in that case from analog to digital, so that it can be processed in the digital computer. Again, after the digital computer, we are going to have a digital to analog converter before it can go to the actuator. So in that case, we can have now a block diagram of a digital control system. So when you talk about a block diagram of a digital control system, after giving that particular comparison, so the block diagram of a digital control system, we can have, we can talk of a reference input here. Reference input. Then from the reference input, we can have a comparator. Reference input, we can have a comparator. Then from there, we can have what we call the controller. Not really the controller, but now the controller has been replaced. So we are going to have digital computer. Then with the digital computer, with this one in this case, we are going to have a digital signal. And from the digital signal here, we can have DAC, that is digital to analog converter. We can talk of digital to analog converter. That, therefore, that one goes to the actuator. We can have the actuator here, which means at this point here, now the particular type of signal that we have is analog signal. Then we can have the processor plant. We can have processor plant in that case. So after that, we can have an output that is now analog. So the output will again be analog. And then along that, there will be a feedback. Along the feedback, we can have the measuring sensor. So here we have the measuring sensor. We have the measuring sensor. And again, after the measuring sensor, we can have analog to digital, because the output that we are going to have there is analog. And therefore, before it can get to the computer, we can have, before it can get to the computer, we can convert it to digital. Then, of course, at that point, we are going to have a digital signal, the digital to analog, not really, analog to digital converter, which is ADC, analog to digital converter, so that it can be compared in that. So in this case, we are going to get rid of the comparator. So here we have what we refer to as the reference input, and here we have a digital signal. So that is a representation of digital control system block diagram. Another way by which maybe you can find it represented, at times it represented by maybe involving the comparator here, but now what you have here is ADC. You have something like ADC here. Then after the ADC, we can have the digital computer, and then from there we can have D to A, DA, digital to analog converter, then it goes to the plant. Then of course, in that case, we have a feedback that goes back to the comparator, which is now reference input. Then the feedback is always negative in order to ensure stability. So it can also be represented in that manner. So that one is the block diagram of the digital control system. So when you talk about the digital control system block diagram, then this control system was simply introduced in order to improve on the tracking performance of the complex systems as opposed to the conventional control system that we know. And the digital computer, in the digital computer we can always use either a microcontroller or a microprocessor, and it will always receive the error, or it, depending on whatever is at the input, it can either receive the error or the reference input alone. And when it receives this, it usually performs the calculation. And there is a program within that is going to perform the calculation in order to provide an output that is near or equal to the desired signal. So the desired signal here, we are talking about the set point or the reference input. So it is going to compare and ensure that the signal that is there is what will determine what kind of program or what type of amplification that will be done. Because we've said that the digital computer in this case is carrying out the function of the comparator as well as the controller. If you look at the loop in the forward and the feedback, then both of them usually contain the analog to digital signals that must provide a means of conversion from one form to another to be used in each subsystem. So in the lower, that is in the feedback, we have the ADC so that it can convert the output that was the output that was initially analog before it can be compared into the digital computer, which will only accept digital signals. So in the forward again, you will also have the DAC that is going to convert whatever comes from the digital computer and then convert it into analog before it is taken to the actuator to ensure that the final control element is moved as in the direction that is dependent on the error. So the device that converts the analog signal to digital signal is what we call the analog to digital converter, that is the ADC. And conversely, the device that will convert the digital signal to analog signal is what we refer to as the digital to analog converter, and that is the DAC. So that is a brief explanation on how this particular block diagram of a digital control system works. Let us look at the advantages. Let us very, very fast look at the advantages of using the digital computers as opposed to the conventional computers that we have for control. One of the advantages, we can talk of the advantages of digital computers. Advantages of digital computers. So when you talk about the digital computers usually record several advantages. So we are going to mention just but a few. The first one, we can talk about the reduced cost. Reduced cost. The reduced cost is as a result of combining both the comparator and the controller so that they form a unit, and in that case they are replaced by the digital computer. So that case, that is one of the advantages. Another advantage that we can talk about is it is always more reliable. It's more reliable. More reliable. That one, we can talk about the effect of, we can talk about it being reliable because, of course, the digital signals are not always exposed to a lot of interference. Another one that is attached to this is noise immunity. Noise immunity. It is always immune to noise. Noise immunity. And when we talk of the noise immunity, then we can only say that it is only the digitized information that can be transported through a noisy channel without having degradation. The other one, we can also talk about flexibility. It's very flexible. Flexible. Another advantage can be, we can also talk about compatibility with other digital signals. It is compatible with other digital signals, so compatibility with other digital signals. Then lastly, we can talk about it is always more suitable for modern control system. Suitable, we can talk of more suitable for modern control system. More suitable for modern control system. It's always more suitable for modern control system. So some of the disadvantages that we may talk about, so we can also mention a few disadvantages of digital computers. Some of the disadvantages of digital computers that we can talk about. The first disadvantage that we can talk about is that they usually require a greater bandwidth than analog in order to transmit the same information. So require greater bandwidth, than analog. In order to, they usually require the greater bandwidth than analog in order to transmit the same information. To transmit same information. Another very important disadvantage that we can talk about is the detection of the signal usually require the communication system to be synchronized, and which is not the case when you talk of the analog. So the detection of the signals, there has to be synchronism. They must be synchronized for that communication system to take place, and that one is not in the case with the analog systems. And when you talk about another thing that you may also notice is that with the involvement of both the ADC and the DAC, you will find that ADC is not always instantaneous and usually needs a two-step process. And in this case, it will bring about the delay between the analog input voltage and also the output digital word. When you talk of the ADC, the analog signal will first be converted to the sample signal and then converted to a sequence of binary numbers, which is now the digital signals. And the sampling rate must always be at least twice the bandwidth of the signal. Those ones are some of the advantages and the disadvantages of the digital computers. Now I want us to look at the digital control. I want us to look at digital control. Digital control. So let us now look at what we call digital control. So when we talk about the digital control, then majorly we are simply talking about the data acquisition system, the DAS. Data acquisition system, or what usually referred to as the data logging system. And this is simply a system that usually scans a number of input signals. And this one is usually from, the input signals are usually scanned. They are usually in form of voltages or even currents. The data logger will sequentially record the information in digital form. The data will have to be recorded in the digital form, and this that we are talking about as the data acquisition system or the data logger usually contain 3 units. So the 3 units that it contains, one of them is what we call the scanning system. Scanning system. It usually contains scanning system. The second unit that it contains is the digitizer. And thirdly, it contains what we refer to as the output devices. Contain the output devices. So those are the 3 components of a data logger. And we've said that a data logger or data acquisition system is a system that usually scans a number of input signals. And this one is usually in the form of analog or in terms of analog voltages or currents. So let's look at a simple diagram of a data logger. Then we can also talk about how it works. So this is a block diagram of a data logger. So the data logger, just as we have said, it usually comprises of one thing is the data scanner. We can call that one data scanner, which has got several inputs. You can have it in terms of several inputs. So input data. Then this one should go to the digitizer. Goes to the digitizer. Then, with that case, what we have here is an analog signal. Then it goes to the digitizer. Then, in that case, we have what we call the output device. We have the output device, and of course, it also has the ability to record. So, has the ability to record. So, in that case, we can have record command. And after that, after it has taken the output, after getting to the output device, it can also come back in order to get the instruction for scanner to the next input line. So this one will come to pick the instruction for scanner to the next input line. Next input line. So that is what the data logger is. Maybe just a brief understanding of what the data logger, how it works. The data logger, or the brief explanation, you find that in the data scanner, the data or the information is presented on a number of input lines. So you have several input lines. The information will be, or the data will be presented on a number of input lines. And this must be sampled sequentially. They must be sampled sequentially. The analog voltages are always sampled at a very fast rate. Of course, they will be sampled at a very fast rate, and the voltage on the line being scanned at any instant of time is applied to the ADC. The digitizer is simply an ADC. The voltage will be applied to the, after scanning, the voltages will be applied to the ADC, where it is converted into digital signal. Then after converting that into digital signal, after the conversion in the digitizer into digital signal, we can also see that the digital signal, which is the digitizer, can also initiate commands which instruct the output device in order to record. And in order to record the data. And then the data logging output devices will give an output, and this one is always in terms of printers, tape recorders, and so on. So that is just a brief explanation on how that one works. The data enters there. Then after the data has been scanned, they are taken to that. And then, of course, at this point, we have digital signal. Then they are taken to the digitizer, which converts them to digital signal before getting to the output device. The digitizer can also inform can also initiate the recording of whatever data that has been processed, and then it can also, after a complete process, then it informs the scanner so that the scanner can go to the next input line. So that is how the data logger works. The data acquisition system, or the data logger, the way it is, can also be very, very instrumental in use as an interface system, that is between the real world and also the digital computer. And this one we can have an arrangement that will facilitate that, whereby we are going to convert, we are going to use the data logger or the data acquisition system as a buffer or as an interface between what happens in the real world and what happens in the processing, or rather the computer world. So we can look at that, very brief diagram of that. So how we can use a data logger as an interface system between the real world and the digital computer. We can have this in order to have that. We can have the diagram in order to see how it can work. So in that case, we have several set points. So the several set points will go to the processor. So we have that one getting to the processor. Then from the processor, we have another set point. We can call it SP. Then at this point also, we can also have another SP set point. So it has got several loops. Then from there, it goes to the multiplexer. Even this one goes to the multiplexer. We know the multiplexer will have several inputs, but will only give a single input at a time. So here we can have the multiplexer. Have the multiplexer. Then the multiplexer go to the ADC. Multiplexer will go to the ADC. And from the ADC, it goes to the computer, whereby the computer will give several outputs. And this one can be in terms of alarms. It can give them in terms of alarms. You can also give it in terms of printers or printouts. You can also have it as stored. You can also have it stored. So you can also have it in terms of storage. Or again, you can also have it at the operator console. Also have it at the operator console. So if you look at this, then you'll find that this one, from that point of the multiplexer up to the ADC, and this one can simply be what we call the data logger. So this one can represent the data logger. It is the data logger. Then, of course, there has to be an address line that is to the computer. There has to be an address line from the computer. So it comes back and it gets into the multiplexer. So this is the address line that will always ensure that there is the communication on how the process is being carried out. So here we have the address line. That is the address line. So that is how we can see. You can see that the uppermost part is the real world. Down there is the computer or the digital computer world. And then you see that the data logger is in between. So it is linking the two different, it is acting as interface between what is happening in the real world and what is happening in the digital computer. So in this case, if you talk about this process, then it is always assumed that that the process is always under control of several loops, and there is always a provision for analog process variable measurement to be available, and this one, they are always available as scaled voltages, and therefore some of the signal conditioning convert all the measurements into a given specified voltage range as required by a data acquisition system. So this one is a simple block diagram that can show how we can always use the data acquisition system, or rather the data logger, as an interface between the real world and the digital computer world. Direct digital control. Direct digital control, or what we shall refer to as the DDC. Direct digital control, or what we shall refer to as the DDC. That is what we can look at, the direct digital control, or what we refer to as the DDC. So in most cases, this one can usually consist of several loops, and this one is aided by the use of the multiplexers and the demultiplexers, which will be in a position to sample the state of many analog and digital transducers at a very high speed. So you can have, we know that the multiplexer can have several inputs, and each and every input should be for a particular transducer, which should correspond to a particular actuator. So in that case, the multiplexer and the demultiplexer will always sample the state of very many analog and digital transducers at a high speed. And this one also will involve very many valves in a plant. So each and every transducer will have its corresponding valve. So in this case, we are talking about trying to control several physical quantities at a go. Because in most cases, when you talk about the control, in the block control diagram, we are always talking about controlling only a single physical quantity, but that is not always the case. Like, for example, you may be talking about a simple robot that is supposed to be carrying out some activity in the shop floor. So if you talk about that, then of course that particular robot you'll have to control its velocity. Also, we can talk of the speed. You will have to control its speed. There are also some things, some objects that it should avoid. So there is the aspect of proximity. You will also have to control proximity. The other one also, it must, maybe if it is picking some objects, then we can also talk about the touch pressure. We can also talk about the touch pressure. So we are talking about speed, the proximity, touch pressure, or any other physical quantity that can be carried out. So what that one entails is that this particular speed, there has to be a sensor for speed and corresponding actuator for speed. There will also have a sensor for proximity and the corresponding actuator for proximity, as well as the touch pressure and any other physical quantity that can be controlled in such a scenario. So when you talk of the digital, of the direct digital control system, then a large number of transducers will always be sited around the plant, and each of these transducer is connected in one input of them, is connected as one input of the multiplexer. The multiplexer is basically an electronic equivalent of a switch with a rotating blade, which usually rotates very rapidly so that it moves from one transducer to another. And at that point, when it moves from one transducer to another, it is able to stay there long enough for an analog to digital converter to sample and as well digitize the analog signal. The digitized, so what we are simply saying is that we have several, we can talk of maybe several, we can talk of several switches, several inputs, we can talk of several inputs. So the several inputs, so maybe we can talk of this one as for a physical quantity, that one as for a physical quantity, and then it is now like a rotating blade, which will make maybe for that physical quantity, and it must be sampled. The sample must also be done in the same sequence that is done in the multiplexer, the same sequence that it will be done in the demultiplexer. And that is how the direct digital control work. So let's look at a block diagram of a direct digital control. So when you talk of the direct digital control, then you can have a plant here. Let's say this is a plant. And then around the plant, it is sited with several transducers. We can have transducers there. And then here we can have what we refer to as the control valves, or rather the actuators. So here we have the control valves. Here we have transducers. So the transducers here are supposed to go to the multiplexer, which is a rotating switch that is going to ensure that they are sampled. So here we have the multiplexer. Then from there we can have this one. Everything that is there should be converted. We have ADC there. And then the ADC goes, in that case, we can have, after the ADC, should also have DAC here, DAC, then the DAC, and then here we can also have the multiplexer, DMUX. Then from the demultiplexer, we can have all those getting into several actuators, and the sampling, as we have said, must be done in the same sequence that it was done at the multiplexer. So here we can have a digital computer CPU, digital computer, can have a digital computer here. Then from the digital computer, so we can have, in that case, we can have this, where we have the data bus getting into that, and the address and control bus in that case. And then in this case, we must be in a position to enter information into that. And in this case, that is the control console. Control console. So we have the control console there. Then this one is, of course, that is the data bus. Then that is now, of course, we must have the address and the control bus. So we can have this one. We've said that they must be connected in such a way that they are sampling. So we can have the address to the computer. So that is what we can talk about as a direct digital control. So when we talk about this, we have several control valves and also several transducers. And in this case, when the CPU has analyzed the data from one or more transducers, then it has to compare with the appropriate set point. So each and every transducer represents the physical quantity that is supposed to be controlled. And in that case, each and every physical quantity will have its own set point. And the set points will be compared with the set point that the physical quantity, whatever we have as the output will be compared with what exists in the program as in the digital computer. So they will be compared. It will compare with the appropriate set points on the computer program. Then it will send signals along the data bus to the valves controlling the system. And when this happens, the digital signal produced by the CPU is then converted into analog signal by a digital to analog converter. And then the analog signal is transmitted to the appropriate control valve via the multiplexer. And when all these are happening, the data will be displayed in the operator's monitor or the VDU, and if necessary, the various set points that are associated with the various parts of the processor can be remotely altered. So you'll find that whatever is here, whatever input that we have at the sensors, whatever is at the sensors, will be taken to the multiplexer, converted to ADC. Then whatever we have there will be compared. At this point, we have a program. It will be compared with what is the set point for each and every physical quantity that we are measuring. So after comparison, it will be taken back through, converted to digital, that is the digital to analog converter, converted to the digital. Then the communication will be taken to the control valve for corrective measure to be taken, and this one takes place through what we call the multiplexer, which will have to sample in the same order by which they were sampled in the multiplexer. So that is how the digital control system, the direct digital control system block diagram works. Another alternative of using the DDC is what we call the computer supervisory control, CSC. We can talk about briefly computer supervisory control, and that is what we call CSC. So when you talk about the CSC, this is an alternative control strategy, and it is always used in microprocessor-based systems. So in this case, the process is controlled by a number of local feedback loops. The process will be controlled by a number of local feedback loops using individual process controllers. The main computer will act as will act or will be used as to do supervisory role, in which it monitors the measured variable. And again, it also has the capability of remotely controlling the set points of the controllers. It has a capability of monitoring, not really monitoring, but remotely controlling the set points of the controllers. This method usually provides the local operator with a control which may have a microprocessor. So maybe we can talk about its block diagram, whereby we can have something like that. Here we have, we can have that, which in this case now, this is the plant. The plant, and then here we have the transducers. We have the transducers. So these ones are transducers. Then, after the transducers, these ones are supposed to come down. This one is supposed to come down. This is supposed to come down. And then here we can have digital controllers. So we can have digital controllers. We have digital controllers. We can have digital controllers here. Those are digital controllers. Then we have the valves. We have the valves there. Then from here, we have this one's going to the data lines. So we can have this moving in that way. Then we can have this. So that here we have the serial communication port. Serial communication port. Then we have a data bus. So this is a data bus. This one goes to this computer, to the supervisory computer. Supervisory computer. Then this one gets information from what we refer to as the control console. Goes to the control console. So this is the control valves. So here we have control valves. Then here we have digital controllers. We have transducers, and then so that is a block diagram, of which in this case here there is transmission, so we transmit. Then in this case this is the receiver, we receive. So basically that is what we refer to as the computer supervisory control. And you'll find that when you talk of this computer supervisory control, each digital controller usually controls one section of the plant. And this is always by means of a closed loop involving its own sensors as well as the control valves. So each controller can always be operated manually in order to give the local operator the complete control of which this one, in order to give the local operator complete control of his own section of the plant. Or this one can as well be done remotely. It can as well be done remotely, so that is involving remote control. So we are simply saying that it can be remotely controlled by means of a communication port, which will always allow the computer either to receive information from the process controllers or to transmit the data to the controllers in order to change the set point. The communication operator usually operates, the communication usually operates in serial mode, and that is the data are sent along a common communicating link or one communicating link, and this one must always be in form of pulses. That one usually occur in form of pulses. So the information is supposed to be sent serially, one bit, using one bit after another, and that one is always set along a common communicating link, and this one usually occur in form of pulses. The digital process controller must usually contain a special interface which converts the pulses it receives in a serial mode along the supervisory serial data bus into parallel mode so as to be used in the microprocessor chip. So that is simply a very simple explanation on how the computer supervisory control works. So generally that is all as far as the digital control system is concerned. And therefore, in our next session, we'll be talking about the SCADA systems.